Okay, what I want to talk to you about now are Zener diodes. All right. Now these diodes, let me draw you a symbol of this. These diodes are able to conduct, they are designed to conduct in both directions. Symbol looks very similar. We've got this break here and this break here. We define the voltage plus minus VD in the usual way, and we define our current ID like so. All right, if we look at the characteristic, and this is pretty much using the second approximation here, looks like this. We've got a plot of ID versus voltage VD. In the forward direction, looks like a regular diode, and if we're talking about a silicon diode, then this value here would be 0.7, about 0.7. In the reverse direction, however, this diode is actually designed to operate, conduct in the breakdown region. Okay, this voltage, this value of VD, okay, is often referred to as the Zener breakdown voltage, and we often refer to that voltage as VZ. Okay, VZ, the Zener breakdown voltage. Now, these Zeners are available with all different values of VZ. So we can have 5-volt Zeners, we can have 10-volt Zeners, and so on. Now, what I'd like to do next is really try to consider, in this block, really a couple of examples. Okay? All right. Let's look at this circuit. I'll draw this circuit for you and we'll make some consideration of it. Okay, so this is an example. All right, let's supposing I have a voltage source here. I'm going to give it a value of 16 volts. I have a 1K resistor here. I put a Zener diode in the circuit. So here is my Zener diode placed in the circuit. And let's say I have a resistor here, which is a 3K resistor. That is now the circuit I wish to look at. And we've got a voltage VO like so. We're going to say for this particular diode, this particular Zener diode here, we're going to say that the Zener breakdown voltage VZ is equal to 10 volts. Okay? Now, looking at that circuit, can we determine whether this diode is actually conducting, okay, whether the diode is operating in the breakdown region? How would we figure that out, okay? Well, one way to look at this would be to imagine taking the Zener out of the circuit and ascertaining what this voltage here is. So if we take the Zener out, then what is the voltage here? All right, so let's imagine doing that. What would the circuit look like? Well, taking the Zener out, I've got my 16 volts. Remember, I've got my 1K here, and I've got a 3K. Zener's out. That's effectively now the circuit, okay? So if I determined what this voltage here was now, let's still call it VO, that voltage would be what? Well, this is a simple voltage divider. So it would be 3K divided by the sum of the two, okay, which is 4K, times that 16. All right, and if we care to work that out, that would be equal to 12 volts. All right, so without the Zener in the circuit, the voltage between this point and this point is 12 volts. All right, if we put the Zener in the circuit, okay, remember, this diode now will conduct, it will basically operate in the breakdown region, and this voltage now will have reached its maximum of what? Of 10 volts. Okay, so if I put the Zener diode into the circuit, yes, it will conduct, and it will have now reached its maximum of 10 volts. All right, I want you to have a think about that problem, and maybe what you could do is you could tell me basically what that diode current is. Perhaps you could work out what that diode current is. Okay. All right, I'll leave you with that problem. Okay, the next example is really, in essence, another clipper problem, but this time we are really using a couple of Zener diodes. So let me draw the circuit. All right, I've got a source here like before. I'm going to say that that's a sinusoidal source. We'll call it V in. Let us say it's got a peak voltage of 10, similar to or the same as what we've had in previous examples. I'm going to put a resistor here. I'm going to say that's a 5K resistor. And now I'm going to put a Zener diode. So here is my Zener diode, all right, like so. And then I'm going to put another Zener diode in the circuit, like so. And this is basically the circuit that we have to consider. This is my voltage, V0 plus minus. Okay? Now, in this problem, we're saying that the Zener voltage, Vz, is equal to 5 volts. All right, remember the characteristic now for the Zener. We're saying both Zeners are the same. All right? So the characteristic is a plot of ID versus Vd. All right? 0.7 in the forward direction. And what we're saying here then is that since Vz is given as 5, that is a value then of Vd, which corresponds to minus 5 volts. Okay. So basically this particular circuit will conduct in both directions. It will conduct in both directions. Okay. Let's consider one direction first. So we're going to consider the onset of conduction, all right, for positive values of V in. So I'm going to bring this V in positive. What value of V in do I have to bring it to for this circuit to actually conduct? All right, that's the question. Okay, let's label this. All right, this is the first diode, let's say, and we're going to say plus minus VD1. Okay. This is the second diode, so plus minus, that's our defined VD2, okay? All right, now let's look at this. Diode number 1, okay? VD1, remember we're talking about the onset of conduction. For the first diode, that would be at this point right here, okay? VD1 would be equal to 0.7. For diode 2, okay, remember we're conducting in this direction, so this diode will have to operate in the reverse breakdown region. So VD2 would actually be equal to, in this case, a minus 5. Okay, minus 5. All right, I think we're ready then to analyze this circuit then for the onset of conduction for these positive values of V in. Okay, all right, so let's take a loop. Standard approach. Okay, so here I go round the loop. By the way, at the onset of conduction though, the current in this circuit, the ID in this circuit is still actually equal to 0. Okay, we're right at the onset of conduction. So as I go around the loop, what do I have? I have V in, okay? Any voltage across that resistor? Well, the current through it's 0, so no voltage across that resistor. All right, so then I come to, I can show that, minus 0. Then I come to this diode, plus, minus, okay, minus VD1. I'll put in the values later so I don't get confused. Okay, then I'm going from a minus to a plus, so that must be a plus VD2. I've completed the loop, all of that is equal to 0. Okay, all right. Now let's take that just a step further. This term goes away, and maybe I'll take these two terms to the other side, okay? So then I get V in being equal to, that term goes to the other side, it becomes VD1. If this term goes to the other side, it becomes a minus VD2, okay? Now I can put in the values for VD1 and VD2, all right? That's these values right here, okay? So V in then is equal to VD1, which is 0.7, okay, minus, let's open up a bracket so we don't lose any signs here, VD2, which is a minus 5, okay? And if we evaluate this, then V in is simply equal to 0.7, a minus and a minus give me a plus, so it's really 5.7 volts. 5.7 volts, okay? All right, well, what about the output? How can we find the output? Well, really, the output is what? It's really going to be this voltage plus this voltage. So look, if you get all confused with this, all we have to do is effectively take a loop, okay, to determine what that output is. So I'll just make a little bit of space over here, okay? So I'm going to write it in this region here. So if I go around the loop, let's say again, what do I have? A minus or a plus to a minus, it means I've got a minus, so that's a minus, if you like, VD2. And then what have I got here? A minus to a plus, that is a plus VD1. And then from a plus to a minus, that's a minus VO, and all of that is equal to 0, okay? So if I took the VO to the other side, which is easy enough, so there's the VO on the other side, that is equal to, what have I got? A VD2 with a minus, so let me put a minus, let me put in the value of VD2, there it is, a minus 5, and then I've got a plus VD1, which is a 0.7, okay? So that's going to give me a V out then of what? 5.7 volts, okay? So that is my onset of conduction for V in going positive, all right? Okay. All right, now let's look at the case then where V in is now greater than that value. V in now becomes greater, if you like, than the 5.7. We are conducting then, we are conducting in this direction. What is the output? So we'll look at that case. All right, so now V in greater than 5.7, all right? Diodes are conducting, so we can say the diodes are conducting. And what do we have? Well, let's once again quickly draw that circuit. All right, we've got V in. Here's our resistor. Here are our diodes. Okay. And what we're trying to do is determine what happens to the output. Okay. So look, this diode, of course, is conducting in the forward direction. This diode is conducting in the reverse direction. And basically, therefore, this voltage therefore becomes fixed. So when V in is greater than 5.7, that output voltage then becomes equal to 5.7 volts. Once again, it's simply from the fact that VD1 equals 0.7, and of course the VD2 is equal to the minus 5. And we just did a little loop like that before to determine the output voltage, and it's the same sort of story here. And so that then is the case when the diodes are conducting. So what have we done? We've looked at the onset of conduction for positive values of V in, and then we've looked at the case, all right, so supposing now we increase V in, the diodes are conducting, what is happening to the output voltage? Now what I'd like you to do at this point is really to see if you can work the case in the other direction. In other words, what value do I have to bring V in to in order for us to conduct in this direction? Okay, so this is the end of block 3. Have a look at that and see if you can now figure out the voltage required for V in to bring the circuit conducting in this direction, and also what would be the value of V out.